Hello, everyone. Welcome to video 6, where we're going to discuss how to differentiate compositions of functions. And this is, I think, something that people seem to struggle with a bit. It's a little more delicate and involved than the last several rules. And there's a bit of artistry into it in that you have to be able to see it, visualize in some sense, or be able to decompose functions into compositions. And that can take some practice. So I'll try to help you through this. And of course, we'll have a lot of opportunity to talk about this and we'll to do several examples. Okay, so where are we at right now? So we have seen that there are several operations we can do to functions on functions. So let me just kind of do this. So given two functions f and g, f at x, g at x, we can do the following. We can add or subtract f at g, right, by just adding or subtracting the outputs at each point x. We can multiply two functions by multiplying the outputs at each point x. And we can divide two functions by dividing the outputs at each point, and dividing the values of the functions at each point. And for each of these algebraic, or arithmetic if you like, for each of these arithmetic operations, we have a rule for the derivative. So we know how to compute the derivative of each of these guys in terms of the derivatives in f and g. Of f and g. And sometimes the rule for the sum is very, very easy. The rule for the product is a little more complicated. The rule for the quotient is very straightforward, right? I guess I forgot one. So I should say also rule 0, k, we can also just multiply a function by any constant by multiplying the output by a constant k. And so that was also an easy derivative rule. So for each of these rules, we have a derivative rule. Sorry, for each of these operations, we have a derivative rule that allows us to compute the derivative of the resulting function in terms of the derivatives of the components of the pieces of f at x and g at x. Okay, so now there's another operation that doesn't come from like algebra, that doesn't come from like addition, subtraction, multiplication, division. That's kind of unique to the function world. And that operation is composition. And the chain rule, what we're going to be talking about the rest of this week, is a way of differentiating a composition in terms of the pieces of the composition, in much the same way that all these other rules we talked about, the product rule, quotient rule, were ways for differentiating the quotient, product, etc., in terms of the component functions, the functions you use to form the new function. Okay, so there is another operation on functions. Oh, sorry. That doesn't come from algebra. Which is called composition. So this is essentially the process of linking two functions together. So function composition the process of linking two functions together. So let me explain. Maybe I should go to the next, I can do it here. So I'll draw my little function machines. So I have a function, which way do I want to go? Start with G. I have a function G, and I have a function F, right? And what I can do is I can input into my function machine G a number X and get out a number G at X. Then I can kind of bring it right beside this machine, this function machine for F, and input the output of G into F. So I can input this number G at X into the machine, or the function machine, the rule for F, to get an output F of G at X. Right here. There. This whole process of inputting X and putting it through the machine of G, through the machine of F, right? That's called composition. We call this process the composition of F and G. So the resulting function which assigns to the number X the number F G at X, F evaluated G at X, is called the composition of F and G. Of the functions F and G. Okay, so let me even underline that. Oops, sorry. Okay, so in our kind of goal, so our goal is, suppose that we have a function h at x, which is the composition of the functions f and g. We want to describe, we want to just to find the derivative, the slope of this function, which is the composition of f and g, in terms of the derivatives f prime at x and g prime at x. Okay, so that's where we're headed. That's what we want to do. But first we need to understand and play with compositions a bit, because to be able to do this requires you to kind of be able to see a composition in a function in some sense, be able to recognize a function as a composition, and that takes some practice. So this is our goal for this week, the rest of this week. Oops, there we go. Okay, so let's just do some basic examples of finding in compositions. And then once we kind of work through some of the examples of compositions, we can talk about the chain rule and see how it goes from there. Okay, so first, we just play with compositions. Just and I am actually lecturing again from the PDF notes, the notes that I've put up with the video 5, section 3.2. So if you want to, so this is section 3.2 in PDF notes for video 5. Just the second half of the notes, but I'm going to write on this yellow pad because it gives me a lot more room to write out explanations, and I don't have to worry about running off the page, that kind of thing. So I hope this is a bit easier to follow than and this app works, like I said, this app works a lot better than the PDF app does. Okay, so examples. So the first thing I want to do is consider two functions, f at x equals 2x plus root x. It's a legitimate function, nice function. And g at x be a function which is x squared minus 7x, right? And what I want us to do is, one, find the composition f of g at x, and two, find the composition g of f at x. Okay, so this is a good exercise because I think it shows you what the trickiest things one of the trickier things about first working with compositions. So I want to just, before I do the example, so maybe we'll start with the first one, f of g at x. What does this mean according to the definition we made above? Where did it go? So f of g at x, right, is the function I get by putting the output of g into the function f, right? So if I'm actually performing that operation, this says to find the value of f of g at x, I first find the value of g at x and then put it in f. So you're actually reading the composition from right to left. And I think that's the first tricky thing about compositions, because you want, we're used to reading from left to right, but when you do compositions, you read from right to left. So you first do the g, first you input into the g machine, output g at x, input into the f machine. And that's the first trickiness with this. Okay, so let's do that. So, and I guess this is like a little remark, function composition is read from right to left. So to form f of g at x, first do g at x, first find g at x, or do g at x, find g at x, first find g at x, and apply the function g at x, apply the function g to x, and then input g at x into f. So I think that's, like I said, I think that's one of the trickier things when you're dealing with this stuff. Okay, so let's do that. So what are we given, right? And I'll go back up here. So our g, right? Our g is this fellow, x squared minus 7x. So, and so you first form that, and then you plug that in to f. So f of g at x, oops, that looks terrible, x is all skewed, is f of x squared minus 7x. So what is f, right, is 2x plus root x, and we're putting in for x, this guy, x squared minus 7x, which is g, right? So we get 2x squared minus 7x plus the root of x squared minus 7x. And you could simplify this a bit, but there's not much you can do. You could write this as 2x squared minus 14x, and then you have this thing under the root, which is this ugliness. Okay, so what are we gonna do? So that's it for f of g at x. Okay, and now let's do the other guy. So number 2, g at f at x. Now remember what I was saying, function compositions are read, right to left. So now we first do f and then do g. So first apply f and then apply g. And then plug the results into g at x. Okay, so our f, remember, what was our f? It's, I'll just rewrite them here so you don't have to scroll up. So recall f at x is 2x plus root x, and g at x was this guy, x squared minus 7x. Okay, so first we do f in this example, and we plug f into g for where we see x. So we use the output of f as the input for g. So g of f at x is g of 2x plus root x. And now, right, I got to compute this guy by inputting everywhere for x in the formula for g, this expression 2x plus root x. So this is, again, a bit of a mess. So it's 2 times 2x plus root x squared. Sorry, no 2 there. Sorry. 2x plus root x all squared minus 7 times x plus root x. And I mean, we could simplify this if we want, but there's not much point. I'll leave it as that now. Okay, so everywhere there was an x here, I substitute in this guy, substitute in 2x plus root x for x, and then you have to square it, and then minus 7, that result. Okay. Now, this is well and good. And again, the way you kind of get good at this and get fast at this is by doing a lot of examples, drilling it in, you know, the process of reading right to left, and just become second nature. So this is probably the easier part. Unfortunately for us, when you need to use a chain rule, you have to not really form the composition usually, but deform or decompose a function into a composition. So you have to recognize a function as a composition of function. You have to recognize a function as a composition of functions and then decompose it. So in calculus, we often need to do the reverse. What does this mean? i.e., we are given a function h at x, which is the composition of f and g, and we have to decompose h. We have to find the f and g. I.e., we have to recognize h at x as a composition of the components f and g. Okay, so this again takes some practice, and unfortunately it takes a little more practice than maybe the other one. Because I think the other thing, once you just remember this, you know, in this last example where you're creating the compositions, right? You just have to remember you need to read from right to left. You first do the function g, and then f in this case here, and then the other way in this case here. But this part requires this next part, decomposing them, requires a little bit more ingenuity. Okay, so examples. So identifying or recognizing compositions. So in the following examples, write the function h at x as the composition of two functions, f and g. So i.e. h at x equals f at g at x. Okay. Now, so here I'll give you the examples and I'll tell you kind of a way to think about doing this. So the first example is going to be h at x. The notes, it's written as y, but that's okay. Equals x squared minus 3x to the fourth power. And then the second one, it's going to be h at x equals the root of x over the root of x plus 3. The first one's a bit easier. Okay, so how do I figure out, so let's talk about number one first. How do I figure out what the f and what the g are? So how to find f and g? Okay, so what does it, again, what does it mean that this h is a composition of f and g? It means I've constructed h by first doing g and then applying f to that result. So when you decompose a composition, what we're going to do is we're going to work our way. We're first going to find f and then find g. We're going to work our way back from the outside in. So actually going to kind of do left to right here. So we're going to first find f and then find g, right? So to decompose h, we will work from the outside in by first finding f and then finding g, so that h at x is f at g at x. Now, here's my trick on how to do this. So here's a trick. To find f, pretend that you are computing, say, h at 1, the value of h at 1 on your calculator. So if I were computing h at 1 on my calculator, what would I do? So I'd first, right, I plug in x, I plug in 1 for x, so I'd have 1 squared minus 3 times 1 to the fourth. What is the last button you would hit on your calculator to compute this? Ask yourself that question. What is the last button that you would hit in your calculator to compute this number h at 1? Ask yourself. And you can even do it. You can even go put this into your calculator and notice what is the last button you hit. What is the last button you would hit, you would press on your calculator to compute the number h at 1? Well, let's think through this. So you first compute 1 squared minus 3 times 1, and the last thing you would do is you'd raise it to the power 4. Right? You'd raise the last button you would hit is raise whatever quantity you found to the power 4. That last operation is this outer function f. It's the last thing you do to get the output. So the last thing we would do is raise quantity, whatever the heck it is, I won't, right? You can, I mean, it's minus 2, but it doesn't matter. Raise quantity to fourth power. We hit the fourth power button on the calculator, right? So, I mean, I guess different calculators have different buttons, but when I was a kid, I guess it was like x to the n or something like this, or button, and you put in a 4, right? So the outermost operation in the composition is the function raised to the fourth power. Is the outermost function. And then what's the function g? What's the inner function of the composition, or the rightmost function, right? It's what you would do first to compute h at 1, right? Then the innermost function, or the first function, is what you would do first on your calculator to compute h at 1, which is computing the quantity oh, sorry, 1 squared minus 3 times 1. Right, so that's if you were computing this guy, remember, where did it go? You're computing this guy on your calculator. The first thing you would compute is 1 squared minus 3 times 1. Then you raise it to the power 4. So the innermost function, or the first function of the composition that you're doing, is this computation on your what you do first on your calculator. So g at x is x squared minus 3x. Therefore, this function h at x is, which was x squared minus 3x to the fourth power, if f is s composed with g, where what we just said, where f at x was x to the fourth, and g at x is x squared minus 3x. Okay, this seems to maybe, I wrote a lot out. You don't have to write all this crap out when you're doing this. It's just for pedagogical purposes that you get a sense for one way of thinking about this approach to compositions, right? And you can, I mean, once you do, it seems like a lot, but once you do, it seems like a lot of work. But once you do enough of these, I think you kind of get used to doing this in your head quite quickly. But let me just say, so what we did is we kind of worked our way this time from the outside in, but by thinking about doing this a computation of a value of a function and thinking about what operations on our calculator will we be doing to find that output. The last operation corresponded to the outermost function, or the leftmost function, and the first operation corresponded to the inner function, or the rightmost function of the composition. So that's what we did. So let's do another example. All right, so it was example 2. I think I called it 2. And so in this case, the h at x was the root of x over the root of x plus 3. Okay, we want to write this as f times g. Sorry, f composed of g at x, and find the functions f at x and g at x. Okay, so again, we can think about, and I'll kind of talk through this and we'll write it all out. H at 1 would be root 1 over root 1 plus 3. And so the outermost thing we would do, so the last thing we would do on the calculator to compute this is we take the root of 1, which is 1, and divide it by the root of 1 plus 3, right? So you basically hit division of root 1. You'd have like root 1 over, hey, make this more interesting, let's put in 2, because then you actually see you have to take a root. So we put in 2, it's more interesting. So you compute root 2 and you divide it by the root of 2 plus 3. So the outermost function, the last thing in the composition, is quantity over quantity plus 3. Right, so you're dividing root 2 over root 2 plus 3. Right, that's the last operation you do. And the first operation, the first thing you hit in your calculator would be compute the root of 2. So the innermost function is g. So h at x equals f composed with g at x. And I want you to notice that the nice thing about, at least with these examples, is you can check your work, right? I mean, it's maybe time consuming, but once you've found the f and g, you can check by what we did in the first set of examples, compute this composition f and g and make sure it's the formula that was given, right? And so we can just check, right? We can check. Same here. So f composed with root x is exactly the root of x over the root of x plus 3, which is what we were given, h of x. So we did it correctly. Now, you don't want to be kind of checking this all the time, probably, but when you first do it, and if you're a little unsure, you can always kind of do the method, the construction of compositions like we did in the first example, right, to verify that you decompose the composition correctly. Okay, so why are we doing all this painful stuff? Well, I mean, it gives you more homework problems to do, but it's not just that. It's so that we can differentiate a composition. All right, so now I'm going to tell you how to differentiate a composition. So this is the chain rule. Okay, so suppose we have a composition of functions f composed with g at x, right? And I'll call this, I should maybe write it as this way. Let me write it this way. H at x is f composed with g at x. Then, okay, the derivative of h, which we can also write in this other notation as ddx of, I should probably use a square bracket, f of g at x, is the derivative of f evaluated at g times the derivative of g. That's what it works out to be. So this is, in words, derivative of outer function evaluated at inner function. Oh, sorry. Times derivative of inner function. Okay, so this is what's a little tricky about it. I think people, we'll do some examples and I'll talk about what the common mistakes are. But it's in other words, to find the derivative of a composition, you take the derivative of the outermost function of the composition, evaluate it at the output of the innermost function g at x, and you multiply that whole thing by the derivative of the inner function g. Now, it's actually, I think, not that, and this may look very strange, but it's not that hard to see why this is true intuitively. Not in terms of graphs so much, but in terms of like practical examples. Maybe I'll talk about that in the live meeting. Like, how can you intuitively visualize this in like special cases? It took me as a student a very long time to understand why this was kind of true in general and what it's saying in kind of a more abstract sense. And so I won't get into that, but it's not something that's totally unbelievable from basic knowledge in some special cases. But we need, so the whole reason that we did this business of decomposing the compositions and identifying the pieces was to be able, what's going to happen in the examples is we're going to be given some function which is a huge mess. We have to identify it as a composition of f and g to apply this chain rule, because you need to know, to compute the derivative of a composition, you need to know what the individual pieces are and be able to find the derivatives, right? So let me just say, so to apply the chain rule, to functions f at x and g at x, right? We need to, to function to a composition h at x, f at x, g at x. We need to identify the pieces of the composition f and g, and then the derivatives. To be able to apply the formula for the chain rule. Okay, so we'll do a couple of examples of this. And this, like, I don't know, I mean, I think this is trickier than all the other derivative rules because of this step that you have to identify the composition. And I think it takes a lot of practice, but it's like one of the most important rules, I think, in calculus, because it's going to come up in really unexpected ways later on, especially when we do integrals. So it's very, very important to get used to this. So we'll do some examples in a bit. All right, so let's do some examples. Okay, so the first example, they actually make it very easy for us because they give us the pieces. So this is a very gentle example, the first one. Okay, so we're told let f at x is equal to 1 over x, and g at x is equal to 1 minus x squared. So we're going to first find the composition f of composed with g at x, and then compute the derivative of the composition using the chain rule above. Okay, so this is not so bad for us. So, okay, f at g at x. So again, remember, to form the composition, you go right to left, first do g, then do f. So you have f evaluated at the output of g, which is 1 minus x squared. So this is f at 1 minus x squared. And f is just 1 over x, so this is 1 over 1 minus x squared. Right? Very nice. Which we can write, if you like, we can write that as 1 minus x squared to the minus 1. Okay, get rid of this little period here. There, okay, we can have punctuation there. All right, so the derivative, oh, that was weird. The derivative f at g at x is the derivative of f, right, evaluated at g times the derivative of g by the chain rule. Right, that's what it says. Okay, so we have f and g. We don't have to go through this process of decomposing now because they gave it to us to begin with. So we got to do the derivative of f, evaluate that at g, and then take the derivative of g, multiply them. Okay, so by the power rule, the derivative of f is the derivative of x to the minus 1 is minus x to the minus 2. So that ain't too bad. And again, essentially by the power rule and sum rule, the derivative of g is the derivative of 1 minus x squared. Okay, so the derivative of a constant is 0. And then, so we just have to worry about the derivative of minus x squared, which is minus 2x, right? So by the chain rule, the derivative of the composition f of g at x is, right, the derivative of f evaluated at g at x times the derivative of g is, so derivative of, right, f is minus x to the minus 2 evaluated at g, so it's minus, and g is 1 minus x squared, right? So it's minus 1 minus x squared to the minus 2 times the derivative of g, which is minus 2x. So we can clean this up a bit. So you have a negative here, and a negative here. They will cancel. So this is 2x over 1 minus x squared squared. Hope that is okay. So derivative of f, right, evaluated to derivative of f, evaluated at g, g is 1 minus x squared. So it's minus 1 minus x squared to the minus 2, then times the derivative of g, which is just minus 2x. Okay, so this one, we got off a little lightly because they gave us the pieces, we didn't have to find the pieces ourselves. And the next one, we have to find the pieces ourselves. So let's set our attention to that for a moment. Okay, so the following function may be viewed as a composition h at x is f composed with g at x. Excuse me. So find f at x and g at x and use the chain rule to compute h prime at x. Okay, so what's the function? So the function they give us is h at x is 9x squared. So we are given 9x squared plus 2x minus 5, all raised to the 7th power, right? Okay, so first find f and g. Now we have to decompose this. Now we play this little calculator game, right? So if we think about h of 2, So you have 9, 2 times 2 squared plus 2 times 2 minus 5, all raised to the 7th. So if you're computing h of 2 on our calculator, the last thing we would do, is raise everything to the 7th power. So the outermost operation is raise to the 7th power. So f at x is, what is it? So raise to the 7th power, x to the 7th. And then the first thing we did, if we were computing this on our calculator, right, would be to compute this quantity, right? 9 times 2 squared plus 2 times 2 minus 5. So the first thing you do is compute this quantity, 9x squared plus 2x minus 5. And h at x is f composed with g at x. Okay, so you can verify this by just computing this like we did in the very first example and making sure that it's the right thing. That is this h at x. But we won't do that. We've done it correctly. And so h prime at x is equal to f prime evaluated at g at x times g prime at x. And so f prime we get from the power in some rule is 18x plus 2. And g prime we get, oh, sorry, that was g prime. I'm sorry. Fix that up. Sorry, f prime is just simple power equals 7x to the 6, and g prime is 18x plus 2. So I was looking at the wrong function there. Okay, so h prime at x is f prime evaluated at g at x, which is 9x, so it's evaluated at 9x squared plus 2x minus 5 times g prime at x. So this is a bit messy. So this is 9x squared plus 2x minus 5 raised to the 6th power times 18x plus 2. And don't try to simplify this, just leave it as is. And so there we go. Oh, this is my little red thing here, the answer. Okay, so again, this was a little bit more involved because we were given this h here, and we had to figure out what the pieces were in the composition. And we did that by playing our little calculator game, I call it calculator game, thinking about plugging in a value and evaluating at the calculator. The last thing we would hit is raised to the 7th. So the outermost function of the composition is x to the 7th. And the innermost is the first series of computations we did, which is 9x squared plus 2x minus 5. Then we have the composition, the chain rule formula, the derivatives we need, derivative of the outermost, derivative of the inner. Then we had computed the derivative of the outer at the inner function and multiply it by the derivative of the inner. It's all good. Okay, so there's one more example that I want to do in this video. And sometimes these examples in the homework you might get involve like functions that are just defined abstractly. And so you should see an example like that. So example 3. And so it's just on page 3 in the notes. So the function h at x is defined in terms of a function f at x. And we're told that h at x is 17 multiplied by f evaluated at 2x plus 1. And the point is find an expression for h at x And it's going to be in terms of f prime. Okay, so like you're not given what this f is. So your answer is going to involve the f. So this question looks a lot worse than it is. It's actually kind of easy because you're already given the pieces of the composition. So let's work through this. So first, actually, we quickly use we can make a quick use of the constant multiple rule. So the derivative of, oh, it's a +1. The derivative of 17 times f evaluated 2x plus 1 is 17 times the derivative of f evaluated at 2x plus 1. So this is the constant, that's the constant multiple rule. And now this guy here, this requires the chain rule, right? This is the chain rule to find this derivative. But we're told that we're given a composition like where the outer function is this unknown function f, and the inner function we're told is 2x plus 1. So we don't have to do any decomposing. We know what the pieces are. It's this unknown function f and this 2x plus 1, which is a line. Doesn't get much easier than that, actually. So this is 17, the derivative of the outer at the inner, whatever that may be, then times the derivative of the inner. But the derivative of the line, 2x plus 1, is just its slope, namely 2. So this is 17 times the derivative of this times 2. And so you can write this as 34 times the derivative of f at 2x plus 1. And like I said, your answer has to involve, it has to involve f. You're not given f. So it has to involve the derivative of f. Because it's unknown. Okay. So I think I'll end this video here. Now the next several examples deal with combining the chain rule with the other rules we've already learned. So actually this example dealt with that in some way too. Because here we had to combine the chain rule with the constant multiple rule, but that's like a really easy rule. The next examples on page 3 of these PDF notes, they involve combining the chain rule with product rule and quotient rule, which is substantially more annoying. So we will go through those carefully. But you should be in good shape to do a lot of the homework now. So thank you for tuning in, and I look forward to seeing you guys in our meeting.